Welcome to The Explainer. So let me ask you a question. How on earth can a drought in one country lead to a global microchip shortage? Today we're going to explore a really fascinating new framework that uncovers the hidden rules connecting our world's most complex systems and, more importantly, why they sometimes break in ways we never see coming.
All right, let's just dive right in. We're looking at a modern mystery, how systems that seem totally unrelated can suddenly cause each other to fail, catastrophically. And I want to be clear, this is not your standard linear domino effect. No, this is something way more subtle and honestly, a lot more dangerous.
I mean, it sounds impossible, right? You've got an environmental problem over here and a high-tech manufacturing crisis maybe on the other side of the planet. But this is a perfect real-world example of what we're talking about, a cross-system crisis. So what is the hidden connection that ties these two things together?
Okay, so it all kicks off with a stressor in one specific area, or what the experts call a domain. In our example, it's an ecosystem, right? And it's being pushed to its absolute limit by a really severe long-term drought.
Now this is where things get interesting. That local problem, the drought, it doesn't stay put. It actually jumps domains. The drought causes water levels in the local reservoirs to plummet, and that means the hydroelectric power plants just can't operate anymore. All of a sudden, an environmental issue has become a full-blown infrastructure crisis.
And here it is, the final piece of the puzzle. You see those gigantic microchip factories? They need a colossal, and I mean a completely stable supply of electricity to run. The second the grid goes down, production just grinds to a halt. And there you have it. A single environmental failure has cascaded through infrastructure and right into the world of technology. This crazy chain reaction actually has a name. It's called a cross-domain cascade. It's how instability spreads between systems that depend on each other but aren't really the same type of thing at all. And a new framework is finally helping us understand the secret rules of how this happens.
So, to really get how these connections work, we first have to understand the basic conditions that allow any system to even exist.
You know, every complex system, I'm talking everything from a rainforest to a financial market, even to your own body, has something called a viability envelope. Just think of it as the sweet spot, the very specific set of conditions where it can actually function properly. Not too hot, not too cold. It's basically the system's own personal Goldilocks zone. Now, this is a really critical distinction. Just because two systems can exist under the same conditions, that's what we call overlap, it doesn't automatically mean they're linked in a dangerous way. For that, you need something else. You need coupling. That's where a change in a shared condition, like energy supply, actually causes a reaction in both systems. So overlap is just potential. Coupling is where the action is.
So how do these coupled systems actually fall apart? Well, it turns out there's a kind of recipe. 3 core ingredients that absolutely have to be there for a cascade to even start.
Yeah, think of it just like a recipe. First up, you need exposure. The systems have to be linked through some shared resource or condition. Second, you need susceptibility. This means at least one of those systems has to be fragile, already stressed out, and kind of teetering on the edge of its Goldilocks zone. And last, you need transmission. There has to be an actual pathway for the failure to travel from one system to the next.
And here's the absolute key. This isn't just addition. These 3 things, they multiply. The total cascade risk is exposure times susceptibility times transmission.
And this is exactly why that multiplication is so important. You could have massive exposure and incredible susceptibility. I mean, a 10 out of 10 on both. But if there's no pathway for the failure to get from A to B, if that transmission factor is 0, then the total risk is also 0. The whole thing collapses. You have to have all 3 ingredients. But hang on, there's more. Even if you've got all 3 ingredients for the recipe, there are 2 final factors that act kind of like a volume dial. They can either turn the risk way down, or they can amplify it into a total catastrophe.
First up, we've got something called damping capacity. The easiest way to think about this is as the system's brakes, or maybe it's shock absorbers. It's the built-in redundancies, the backup plans, the flexibility that lets a system take a punch without completely falling apart.
And then you've got the other side of the coin. Synchronization. This is the ultimate amplifier. It's that perfect storm scenario where a whole bunch of different connected systems all become fragile and vulnerable at the exact same time. This is often because they're all being hit by the same big external problem, like, say, climate change or a global recession.
So you basically have this constant tug of war going on. Damping is always trying to absorb shocks and contain the damage, right? It lowers the risk. But at the same time, synchronization is lining up all the vulnerabilities across the entire network, creating the perfect conditions for one tiny failure to bring the whole house of cards down. So when you put all of these pieces together, the core recipe and these volume dials, what you get is an incredibly powerful new lens for actually seeing and classifying risk in our crazy interconnected world.
What's so cool is that this framework lets us map out the different risk states that a network can be in. A group of systems could be safely buffered, highly connected, but with really strong brakes to stop any failures. But as that damping capacity gets weaker and synchronization gets stronger, it can shift all the way over to being cascade-prone, just sitting there waiting for a trigger. And look, this isn't just some abstract theory. It's a really clear, practical way to diagnose the hidden risks all around us. It works for ecological collapse, for infrastructure blackouts, for financial meltdowns, and even for how diseases move through the human body. It gives us a common language to finally talk about why these huge systemic failures happen.
Ultimately, by understanding these hidden rules, the recipe for how things fall apart, and that battle between the system's brakes and its amplifiers, we can start to actually see the connections that were invisible before. It's like having a new map for a world that's always changing. And that leaves us with one final, and I think pretty critical question. In a world this connected, what is our biggest blind spot?